Action potentials in myocardial contractile cells. Do you know what prevents tetany from occurring in cardiac muscle cells? In this last episode of this Chalk Talk course on action potentials, we'll wrap this up with a series of events that occur during and following an action potential in myocardial contractile cells. Sustained or tetanic contraction of myocardial contractile cells would be life-threatening and is prevented by special properties of their action potential, leading to a significantly longer refractory period and preventing re-excitation before muscle contraction is over. The resting potential of myocardial contractile cells is around -90 millivolts. It's almost exclusively maintained by potassium ion efflux through delayed rectifier potassium channels. In contrast to other cell types, action potentials in myocardial contractile cells aren't triggered by a transmitter, but by electrochemical stimulation. The depolarization of a neighboring cell results in some positive ions moving from their cytosol into the myocardial contractile cell through gap junctions. Thereby, the excess negative charge decreases and the membrane potential increases. If it exceeds around -65 millivolts, the potassium channels close and the voltage-gated sodium channels open. These sodium channels enable the rapid influx of sodium ions into the cell, leading to rapid depolarization. Reaching a membrane potential of about -40 millivolts, the sodium channels close again, resulting in the termination of sodium influx after only approximately 1 millisecond. The maximum attainable membrane potential is approximately +20 millivolts. As with neurons and skeletal muscle cells, repolarization follows. However, initially, only partial repolarization takes place in myocardial contractile cells. A transitory efflux of potassium ions through transient and ultra-fast potassium channels in conjunction with an influx of negatively charged chloride ions lowers the positive intracellular charge. The membrane potential decreases to about 0 millivolts and is maintained for approximately 200 to 400 milliseconds in the plateau phase. For this to occur, the repolarizing potassium and chloride currents are counterbalanced by the slow influx of calcium into the cell. The responsible L-type calcium channels are also voltage-dependent and activated at values exceeding -40 millivolts, but open with a significant delay. As soon as the calcium channels close, the repolarizing ion currents dominate again, resulting in the final repolarization of the myocardial contractile cell. During this part of repolarization, the rapid and slow potassium channels are primarily involved. Also, the delayed rectifier potassium channels contribute to restoring the resting potential in the myocardial contractile cell. In cardiomyocytes, after hyperpolarization doesn't occur, similar to skeletal muscle cells. Instead, a long refractory period ensures the correct functioning of myocardial contractile cells. The absolute refractory period, during which sodium channels are inactive, lasts until the end of the plateau phase. During final cell repolarization, the voltage-dependent sodium channels return to their active state. However, they're only completely activatable once the resting potential is re-established. To sum it up, there are several similarities in the formation of action potentials in the 3 different cell types that we've discussed in this Chalk Talk series, namely neurons, skeletal muscle cells, and myocardial contractile cells. Check out parts 2 and 3 of our course if you want to learn more about how the action potential of neurons and muscle cells differ to that of myocardial contractile cells.